Okay, this is off.
Gee, which mic is on? This one.
Perfect. So easy. Okay.
So, okay, welcome.
Whoa, 1 second.
Not yet, not welcome yet.
You are not welcome.
Just one, we confused everybody terribly with this picture thing, and it got cloudy, and it got late, and so tomorrow morning, after the morning session, please be here, because before we walk over to the coffee break, we'll go out on these steps in the sunshine, might be cold, take a picture.
Wait,
And look, here's the people we're with. Sorry?
remind them they have to have their beanies.
Oh, right, and we have the box attached here, and so if you did not get one of these excellent beanies, by the way, when I was young, a beanie only went on the top of my head, so I don't know why this is called a beanie, but it is. Anyway, so, well, for those who speak German first, they want to anyway, so if you don't have one of these, get one in time for the picture, and look, the rest of the audience showed up during that excellent song.
So you talk about beanies and they're all in.
Okay.
Okay, welcome to this afternoon session back at Philips here, and our first speaker in the research section is Manuel. Relationships.
Excellent. Relationships, yeah. Yeah, thanks first of all for the opportunity to present you a little bit what I'm working on. So first of all, let me give you a little bit of context. So I'm a PhD student at the MPIA, and I'm part of this PROMISE working group, which is led by Joni Kainolainen, who is also my supervisor. And what we're trying to address in this, or what we're trying to do, is really build a galaxy-scale view of the internal structure of molecular clouds. And we also try to confront, or rather test, a little bit this paradigm of the turbulence-regulated interstellar medium and the star formation model on the scales relevant for entire galaxies. So the main data product of PROMISE will be a new dust extinction survey, a new dust extinction map, and we will really cover a significant portion of the inner galaxies. So it extends from plus minus to 40 minus degrees in galactic longitude and plus to -1 in galactic latitude. We will be able to probe structures up to until 7 kiloparsecs. And the nice thing will be that up until 5 kiloparsecs, we will still have a resolution of 0.1 parsecs, so basically the core scale. Let me show you how this is done. So basically, PROMISE is a combination of extinction mapping in the near-infrared and in the mid-infrared. And I'll illustrate this here with an example of a typical infrared dark cloud. Seen above here, the Spitzer 8 micron image, and below in the near-infrared, an image of the VVV survey. You can see here the corresponding extinction maps, and then you immediately see the advantages and the disadvantages of the two extinction maps. So at the top, the mid-infrared gives you really the higher column densities, but you lose the extended structure, so the background basically. And in the near-infrared, you basically have much worse resolution, spatial resolution, but you get this more extended diffuse structure. And what PROMISE does is basically combines those two efforts. So you get basically the best of the two worlds. So you're sensitive to the higher columns while retaining this more diffuse background. And of course, we have this 2 arcsecond resolution from Spitzer. And why is this important? So let me show you here. This is this typical cartoon of the Milky Way. And what I highlighted here is what we were up until now able to probe in 0.1 parsec resolution or better with Herschel. So dust emission. And let me zoom into a little bit to show you what PROMISE will be able to do. So we will really cover a much larger area of the inner galaxy, and the important part here is really up until 5 kiloparsecs we have 0.1 parsec in resolution, and of course better the closer we get to the sun. But another nice thing is that this neatly overlaps with existing wide field line emission survey, like the Galactic Ring survey and the new APEX survey called SETI-GISM. So both is a line emission of 13 CO. And basically what this will allow us, and this is my project here, again to address these questions, how is about the internal structure of molecular clouds? So which physical processes are responsible for shaping them? Is it mainly turbulence, mainly self-gravity? And we really also want to address the importance of the large-scale kinematics of the molecular clouds through the fragmentation. And we also want to address this, this prediction of turbulence-dominated gas. I flash here an example of this. So basically this correlates how the density variance, in our case this will be the width of the column density distribution, probability distribution function that we get from the dust, so from PROMISE, how this relates to the turbulence energy. So here basically the sonic Mach number is here the proxy that we'll get from the width of the CO emission line. And basically such a prediction would give you something like that. So on the x-axis you have the sonic Mach number plotted against the density distribution width on the y-axis. Here the blue curves show you the case where basically magnetic fields are important, and the dashed and the solid lines are just for different turbulence driving parameters. And this here would be the case where magnetic fields are negligible. And what we are confident that we will be able to do with PROMISE is to populate this with hundreds of data points, so hundreds of molecular clouds, and to really try to test such predictions, and in the best of cases also severely restrict the possible parameter space of this, to also then restrict kind of the physical processes that can be responsible for this. So this is also kind of our plan. The first step to get the density variance and to find those clouds, this will be done by PROMISE. And the second step is then really to find the best matching velocity components for each of those clouds. And this is what I focus on. And of course, the one problem is we want to do this in an automatized and in an efficient way. And these line emission surveys, I mean, those are a huge surveys, like millions of spectra. But fortunately, this year saw the release of a nice new algorithm called GaussPy, which automatically decomposes spectra into Gaussian components. And it is basically used in something called derivative spectroscopy. I will explain this in the next couple of slides. It also uses machine learning in this basic sense that you feed this algorithm a training set and it finds out 2 parameters that it needs to do this. And it's also optimized really for multi-core processing, so it means it's very efficient and very fast. But how does it work? So you see here a typical spectrum, velocity on the x-axis, intensity on the y-axis of spectrum of the GIS data. And what we want to do, so GaussPy uses higher derivatives, so basically it finds extreme values, it goes up to the 4th derivative. To do this, you want to smooth the spectrum because otherwise you will hopelessly amplify the noise that is here in the spectrum. And now you have to find out how to best do this. So in red, I plot here like the 2nd derivative of this very spectrum. And in this case, we use the higher value for the smoothing parameter. In comparison, this would be like a lower value. And you see immediately the difference. So here we are more sensitive to these broader structures, and we don't really care about the noise. Here we get the thinner structures, basically the narrower components, but we also have the noise wiggle still there. But let me show you, let us go with this one, how GaussPy proceeds. So the user chooses a signal to noise threshold for the original spectrum and one for the 2nd derivative. And GaussPy will then give initial guesses for those points in the spectrum where both cross this threshold. And this is really the essential step to get this initial guesses right, because what you can then do is basically make an intermediate fit, and in the next step subtract this intermediate fit from the original spectrum and run the whole procedure again on the residual, but with a different moving parameter. And what this gives you is a nice decomposition of the spectrum where you get those narrower components as well as also the broader Gaussians. And here's an example we ran GaussPy on the GIS dataset. So this is the original spectrum from the GIS dataset. It wasn't smoothed in any way. And you see that GaussPy is capable of of dealing with those body blended components. Here is another of those examples. And we chose in the beginning a test region centered around 19 degrees of galactic longitude. And what you see here is a 3D volume rendering of the original data set. So you get the galactic longitude on the x-axis and the velocities on the z-axis. And this here is basically what we recreated from the GaussPy decomposition. And you can see here that with the Gaussian components, we are basically able to, I would say, get all the important structures. This is also illustrated here in the zeroth moment map, so the integrated intensity. To the left, again, the original data set. In the middle, our GaussPy decomposition, and to the right, our residual. So we also basically get, I would say, most of the flux. But let me show you how we will deal with this finding the best matching velocity component. So for this, I zoom here in. This would be basically a typical infrared dark cloud. Again, this is what it looks like at Spitzer 8 microns. With PROMIS, we will really get like these extinction features. And if I overplot those now on the first moment map of our GaussPy decomposition, you basically see like you get a general gist of what the velocity is for this, the dominant velocity is for this structure. But of course, it is more complicated than that. If we zoom into individual pixels, more often than not, we have like multiple components along the line of sight. And this is now work I'm currently working on, so to really find a pipeline to deal with those ambiguous cases. And we will try to implement morphological matches, use distance information, and also information that's out there on dense gas tracers to help us deal with that. But for the last couple of slides, I actually want to zoom out again to a more global view. So this is our test region centered around 19 degrees of longitude. And I now put this a little bit into context. So this is now the entire GIS data set, and it extends here from 14 degrees galactic longitude to 56 degrees of galactic longitude. It's again a zeroth moment map, so the integrated intensity. And we actually ran GaussPy on the whole data set, and what you see here is the comparison of our decomposed version. And I would say we are really able to recreate this data set with our Gaussian components. This is also seen here in the position velocity images, where you see basically that with the decomposed version, we basically retain it is, I would say, almost indistinguishable. But what I want to illustrate here is with this Gaussian decomposition in our hands, we can actually try to go beyond this more simple analysis. And what I plotted here is basically the integrated emission of the decomposed Gaussian components, but plotted at the centroid velocities. And what you see, you get a feeling for the complexity inherent in the data. And I think we are in a position now to really deal with this complexity and do it more justice in the data. That means we can try to analyze the velocity structure in more detail, find out about velocity gradients along the clouds, and also how the velocity dispersion changes along the clouds. This basically brings me to my last slide, which is more of an outlook. So we're currently really heavily working on getting this pipeline going that we will need to get like best matching velocity components to this to the density information. But we're also working, this is work done together with Jonathan Henshaw to really try to efficiently produce this training set that is needed for GaussPy, so that this is also easily basically applicable to other line emission surveys. In the longer run, we're trying to do comparison with MHD simulations, and of course, with those huge data sets, there are lots of potential follow-up and spin-off projects for PROMIS as well as for the Gaussian decomposition results. With this, I'd like to thank you for your attention.
Thanks a lot, Manuel. So, open for a few questions.
Well, this looks very promising.
Thanks.
But some line profiles are not intrinsically Gaussian. For example, when you have a superposition with hyperfine components, or when you're optically thick, would you have the flexibility to deal with those kind of line profiles?
So we're trying actually to implement this in a way. I mean, obviously it heavily depends on how the training set. I mean, you supply it basically with spectra and decompositions that you think are right. And GaussPy will then use its smoothing parameters to try to recreate this very decomposition. In the current case, we're only using it for CO line emission, where this is not that big of a problem. But we're definitely aware of that and try to also implement this so that this will be possible. Treated completely independently. So there's like each fit is completely independent.
So if there's like smooth transition over like one beam size, then you could fit that with different components?
What do you mean with the smooth?
In one pixel you have 3 components, and the pixel next to it you have 1 component, the pixel next to it you have 3 components. That would be
That could definitely happen, yeah. So this is then you would definitely in those cases also have to analyze the data and to really make sure that this is in your interest, that this basically, how this is dealt with, yeah.
Other more questions?
Yeah. In the same realm of the previous questions, what about if you have a superposition of a narrow Gaussian and a broad Gaussian? Can that handle that case right now? And I can top it off if on top you have an absorption feature.
It cannot deal with absorption features, so this is a problem that we have, but it definitely can deal with those when it's like blended with narrow components and more broader components. Obviously, a problem inherent in the Gaussian decomposition is that it's degenerate, so you more often than not have multiple ways how this can be fit, and this is then really where the training set comes in, that you steer it in the direction that you want it to happen.
So basically, it knows about the math, but not about the physics.
Yeah, that's definitely how it is.
So training set versus number of spectra. How many training set spectra and how many you fitted for the whole survey?
I mean, for this whole survey, and this is actually the nice thing, we only used like 1,000 spectra from around galactic longitude 19 and then applied it to the whole survey, and this was enough.
How many is in the whole survey?
I'm thinking at least 2 million, if not more.
To 2 million, that's a good ratio. Any other question? If not, then let's thank Manuel again. Thanks a lot. And I think we have our first session of introductory talks, so I guess you have them on your laptop. And I asked Jens, Yuan, Mark, Perry, and Mia here. Yes, no, okay. So then it's...
I have to leave that now. So
Sorry?
this is what we're going to be done instead.
Oh, Doug, and so Doug, you're Nia.
Yeah, Don, you're not Nia. Sorry. Sorry. I'm just
That's all right, don't worry.
A very tall version of it.
So could we have a little bit of light? I think that's for the
Can't
intro.
see. Everything
would be
looks
good.
the same up here.
This was the problem yesterday. There's like no intermediate. Is Sean still here? Sean, are you there?
Who's first?
He managed to get
How did
something.
you want to
Sorry, the first is Jens.
There you go. Sorry, I didn't see you. It's so dark.
You want to do it like this? I'll send them an email. See if they can come.
Let's see whether we see the presentation. If not, then we may turn it up. I think it's nicer to see the people. So 2 minutes, you know what 2 minutes are, isn't it? Or do you want a reminder?
Do I have a choice?
I could time it properly. I think it's exaggerated, but I know you're... it's aber hier akkurat, you know. It's okay from the light. So Jens,
Yeah, I don't need anything more dark. So my research is essentially into the dense gas in the Milky Way, and also my research interest also goes over to the galaxies nowadays. Essentially, what I'm doing in the Milky Way is to a large extent to study self-gravity of molecular clouds and to figure out whether they are self-gravitating or more than self-gravitating or whatever. Doing this throughout the disk of the Milky Way, but also in the center of the Milky Way, in the central molecular zone, with a 30-hour ALMA project that's still ongoing. And essentially what I find is, can you see this at all? I hardly cannot see. So the point is that there is this cloud of points here down in this gray area, and these are overbound dense cores, so to say. So it's essentially like you have a dense core which is not collapsing, it's kind of levitated, it should collapse, and it doesn't. And that's very weird, and it's by a factor 10 or so. So we still look for theorists to tell us how this is possible, whether it's magnetic fields or something else, or observers telling us what are we doing wrong here. That's by a significant factor not known. What I'm also doing is to study, to calibrate essentially ways of studying dense gas in other galaxies. And I again come to the conclusion that we don't really know what's happening in galaxies. For example, here I'm trying to calibrate the density traced by HCN. If you ask extragalactic observers, that's supposedly tracing gas at 100,000 particles per cubic centimeter. Here I can show you it's tracing 1,000. That's 2 orders of magnitude difference. Makes all the difference if you want to study free-fall timescales, etc. in galaxies. Thank you.
So next one is Yuan.
Yeah.
Hi everyone, so my name is Yuan Wang. I'm working on the SOAR project at Heidelberg. I'm a postdoc there. And here I'm showing you the H1 channel map there. And down here at the continuum, 1.4 continuum gigahertz emission feathered with VGPS image. And for the continuum data, we extract the continuum sources for more than like 10,000 sources. And then for like more than 3,000 sources, we can derive a reliable spectral index, which means we have detection along the whole 6 spectral window between 1 to 2 gigahertz. And just to show you a simple distribution of how the sources are along the galactic longitude and galactic latitude. And most of the sources are relatively uniform distributed along the latitude, except that the very extended sources, they are really concentrated along the latitude. Also for the spectral index, they are like peaked around -1 and 0. And for the H1, we select one giant filament to study the H1 self-absorption. So with some assumption, we can fit the absorption baseline with the polynomial, and with some assumption of spring temperature, we can derive the column density map, which is shown down there. And so we can compare with the PDF from the molecular cloud, and also we can compare the kinematics. The simple one is the peak velocity. And then we can see that on the filament on the right side, the peak velocity between the CO and the H1, which is shown in black, are different, but they are very similar on the left side. So maybe it's different evolutionary stage, maybe it's due to active star formation. I have a poster down in the other house. If you are interested, come talk to me. If you are interested generally, also come talk to me. Thank you.
Should be good enough. Okay.
Marguerite is our next one.
Okay. You get a laser on this?
There's another one I think maybe that might work. And the second
I just didn't know which is which here.
Is that one
the
working?
red one?
Is it doing anything?
Yeah. Okay. Okay. In 2 minutes, I'll run you through what I've been doing for quite a while. This is a map of the Milky Way, face-on view, viewed from the North Galactic Pole. And every source on there is a high-mass star-forming region for which we have a trigonometric parallax measurement. So here's the galactic center, and here's the sun. And you can see we're very accurately tracing the spiral arms in the Milky Way. But as an outgrowth of this project, we've developed a technique to try to improve distance estimates for other sources for which we have not measured a parallax. Okay, so basically, along any spiral arm, pick this one here, we know the trace, basically, of coordinate and velocity along the arm. And if you could match that with the coordinates and velocity of a source from a catalog, you could be pretty sure that it's at about this distance from the sun. So we've developed a Bayesian program to try to optimize this. Here's a longitude velocity plot of carbon monoxide emission, galactic longitude velocity. And you can see spiral structures in this. For example, the red curve here is the Sagittarius spiral arm. So let's say we have a source, G43.03, which has an LSR velocity of 56 kilometers per second. That's where it would be. If you run our program, which is available on the web at the Bessel website, the Barnes Spiral Structure Legacy Survey website, you get a probability density plot, and it's got several terms in it. For example, the green line here is the standard kinematic distance, which is, of course, double valued in the inner galaxy. The association with the spiral arm is the red curve here. There's a hint of, a match here. There's a very good match with the far portion of the Sagittarius arm there. You can put other information into this, which is on here. You multiply the probability densities together, and you get a combined probability density, which is this black curve, which says this source is about 8.5 kiloparsecs, with pretty high confidence. So the last slide here, I'm just going to show you a visualization I tried to put together of the Milky Way by taking these catalogs of sources, which are all sources that are young objects associated with high-mass star-forming regions, which should be associated with spiral arms. Ran them through the program and sprinkled 5 dots for every one sort of around to try to give you a better visualization of the fact that, there probably are multiple sources in any molecular cloud that are forming stars. And that's what you get. The dark blue points are the ones where the program was pretty confident that it could assign a spiral arm and get a good distance. The cyan points up here are where it was not confident it could do much. Over here, on this side of the dashed red lines, are sources from the southern hemisphere where we haven't yet measured parallaxes to determine where the spiral arms are. And so essentially this information is almost all kinematic, and you can see it doesn't work very well. Okay, that's about it.
Hi, so my name's Perry Hatchfield. I'm a graduate student at the University of Connecticut working with Kara Battersby and the CM Zoom team. This is my obligatory Herschel 3-color image of the inner few hundred parsecs of the galaxy. So I've been working as part of the CM Zoom team, as I said. I think Danielle Callanan showed this figure yesterday, but I'll show it again. These are the pointings of the 500-hour SMA survey of dense core and structure in the inner 500 parsecs of the galaxy. So it turns out there's a wide range of structures, filamentary and dense cores, and all sorts of stuff over different spatial scales ranging from sub-parsec to tens of parsecs and beyond. So we wanted some way to, given all of this great data, characterize those structures in some sort of self-consistent and complete way. So I've been working on an implementation of the dendrogram algorithm with some variations in order to take into account the widely varying noise levels across the survey. This is on the top a image of the selections from the CM Zoom survey focused around Sagittarius A star, which is that particularly noisy bit sort of in the center. I could probably point at it, but I don't want to figure this out right now. And on the bottom is the same contours put against, the same dendrogram leaves put against the Herschel 250 micron dust continuum. So in addition to that, I also kind of want to get a sense of how the accuracy of these dendrograms falls off as a function of the pretty expensive parameter space that they can take into account. So this is just a sample of that with a few different choices of the minimum delta parameter, which characterizes how different the leaves of the dendrogram have to be from their branches, and also as the minimum delta. And so as you can see, they sort of fall off, and we want to get a sense of exactly how accurate this catalog that we end up putting out is. Thank you.
Last but not least, Doug, it's your turn.
All right, thank you. So the scope of this meeting extends from very dense, dark things that are forming stars to the diffuse interstellar medium. I'm going to talk about the extreme diffuse end of it. So apologies for those who just spent the last hour and a half with me talking about a 3D dust map. For the rest of you, we did this project using 1 billion stars from pan-stars and 2 mass, where we, for each star, ask what the posterior on distance and reddening is, given some stellar models, where they should be in color space and so on. And then we can group stars 100 or 1,000 at a time into a line of sight and ask what distribution of dust along the line of sight is most consistent with the data. And then out of this, from these billion stars, we can form a dust map with about 3 million angular pixels and 30 distance bins. So think of this as the crude first step in a long journey to try to make better dust maps. Now, I know you worked hard to get the lights on, but it does look better with the lights off. So we're flying towards the sun. There goes the sun. Look out! And now we're heading towards Orion. And, MON R2 is about twice as far away as Orion. So we fly through Orion to MON R2. Now we're beneath the disk of the galaxy. We're going to go up through the disk and go up high above the galaxy and swing the camera around, look back down. And what's kind of cool here is you can see features of the Milky Way disk that you cannot see from our location here by the sun. For example, we just stop about here. See these holes in the disk? From this angle, there are obvious holes in the disk, like something blew up and pushed the gas aside. But as the camera comes back down towards the sun, they disappear because we get into an angle where we can't see them. So it's nice to be able to see the Milky Way in 3D. We hope to produce a map like this that goes out farther. We only trust this to 4 or 5 kiloparsecs. We'd like to go out much further and have much better distance resolution in the future. Thanks.
Thanks all for all these introductory talks, and I think we are back to research talk now. And I think it's Charlie.
And we can turn the lights on if you want.
I don't know how.
I think it's right, podium, oh no,
I did email him, but he did write that.
Yeah, it's otherwise audio control. He's not here. Or screen blinds, lighting.
But I can't turn them to
The
medium.
single button.
Let me just try from the back.
Did I give you 2 minutes after 10?
Yeah. What's that?
2 minutes after 10, so I think it's 12 plus 3, isn't it?
Well, if we first see if this works.
Yeah. We'll
Didn't
take
work
every
when I
minute.
tried it out before. No, it doesn't work. Why is that? Why isn't this working? You go on the display? Yeah, I just went through this with Alyssa because it didn't work right away. Let's try it here. So you want a display?
So if you have the preferences.
Not many degrees of freedom.
There's the front.
Should be this one.
No, it's not that.
Show mirroring option. Go to this show mirroring.
Well, yeah, again, Alyssa. So.
Like
Charlie, what's going on?
Well, it kind of worked. I
Want
turned
me
up
to
the
do it?
nurse, but yeah.
Okay. Why is there nothing
Well,
there?
let me see. Good question.
Try it
This-
again.
this might-
We just changed one thing. Whether that helps.
No,
It's the same thing.
So what's your magic now?
Well, there's something on the,
Yeah, but there was at least something on the screen.
yeah, at least there.
Wait, why are you using this? Where's the HDMI? Does somebody have the HDMI adapter for this?
This one can probably do the HDMI.
No, it doesn't have a direct. We had a dongle for the HDMI. Somebody have that? No. Silence. Sarah is not here.
You had this before, wasn't it?
The whole
There was the dongle
projector
for the
went
HDMI, wasn't it?
I fixed it. All right, I fixed it.
What did you do?
Don't ask me.
All right.
It's displays still.
So Charlie
There
talks
we go.
about the
All
one
right.
and only local truth. Let's see.
Their pointer, that works? Yeah, so star formation and GMCs, the local truth. First, I want to list my collaborators who worked on some of this that I'm going to talk to you about today. And I'll start out by just saying a very few words about the context, star formation across cosmic history. And one of the things we have to realize is that one of the great challenges that we face is trying to determine the rate at which interstellar material goes into stars. That's the star formation rate. And we want to do that because the SFR is the primary metric for describing galaxy evolution through cosmic time, as you can see on this fairly famous diagram of star formation rate, volume density as a function of Z. Now, so if we want to understand galaxy evolution as well as star formation, we need to try to understand what the physical processes that set the star formation rate are and how they control then galaxy evolution. So Martin Schmidt was actually the first person to postulate that perhaps there's a connection between the rate of star formation in a star formation region and the density of gas there. And Rob Kennicott applied this idea to galaxies, and he came up with this correlation where he plotted the surface density of the star formation rate versus the gas surface density and found a nice nonlinear correlation. So this is one of the primary extragalactic metrics for understanding star formation and galaxy evolution. And the other famous one is here, which is this thing called the star formation main sequence, where you plot the star formation rate, the global star formation rate, against the total stellar mass of a galaxy. And what you find is that the star formation rate is basically linearly proportional to the total stellar mass of a galaxy. But there's an interesting thing that happens. The coefficient here is a function of look-back time of Z. Now, I won't be able, I'm going to now describe observations of local clouds that pertain to this and help us decipher both these diagrams within 10 minutes. I won't be able to apply what I told you to these, but you can always ask me about that later. So, the local truth. When we look at local clouds like these two here, which are very close to the sun, at the same distance from the sun, roughly the same mass and same size, you can see they have very, very different star formation rates, so they're excellent laboratories, the local clouds, for trying to understand what determines the star formation rate. The reason that we can do so well locally is that we can get direct measures of star formation rate by directly counting the numbers of young stellar objects, and we measure their ages, so we get the star formation rate. And also we can do very well measuring the sizes and masses of clouds because they're well resolved, and we can do this in molecular lines, or even better, with resolved measurements of dust, from which we get column densities, and with a simple assumption of a gas-to-dust ratio, we can get good masses and also the good sizes. So one of the questions we might want to ask is, we go through this exercise for all the local clouds, do we find that the Schmidt law exists in the local Milky Way? And the answer is quite clearly no. There is no Schmidt law for molecular clouds in the local Milky Way. And you can see here, I plotted the surface density of star formation versus the surface density of gas for the local molecular clouds, and they're not correlated. This turns out to be a key to understanding the Kennicott-Schmidt law,
And again, I don't have time to go into that in 10 minutes. So I want to also, though, say that a Schmidt-like law does exist within a molecular cloud on subcloud scales. And I'll show you that here. These are 3 molecular clouds that we studied with Herschel and Planck, and also have very good inventories of young stellar objects. And you can see the Schmidt laws. Here we use the number of protostars as a proxy for the star formation rate, and the extinction as a proxy for the gas surface density. And you can see there are very nice power law relations, Schmidt laws on these clouds. The slopes, the beta, are actually steeper than what we saw in the extragalactic case. And the fact they can get pretty steep, and they vary from cloud to cloud. So one of the things we wanted to understand is what's responsible for this variation in the Schmidt law in local clouds. And the key to that turned out to be looking at the structure of the clouds. So I'll show you that here first. How do we measure structure of clouds? Well, the typical metric we use is the PDF. And on the diagram to your left, you see a compilation of PDFs determined from Herschel and Planck. And what did we learn is that for molecular clouds, the PDFs are power laws. Not log normals as far as we can tell, but power laws above the molecular formation limit of about 2 magnitudes. Moreover, what we've learned is that the power law index does vary, and although you don't see it so well in this diagram, it's very clear here on Uni K. Narayan's study of profiles in local clouds, that star-forming clouds have flatter PDFs, i.e. more material at high column density than non-star-forming clouds. So if we now go back to our Schmidt laws and the 3 nearby GMCs, and we look at their PDFs, you notice one thing, like I said, the PDFs are very well described by power laws, actually better described by power laws than even the Schmidt law. And you notice that just as a Schmidt law can vary, especially if you compare Orion and the California, you can see that the PDFs, their shapes also vary, and it appears that the Schmidt law, on subcloud scales, its slope depends on the slope of the PDF of the cloud. We can understand that a little bit more clearly when we remember that the star formation rate, the global star formation rate, is the integral of the Schmidt law times the surface density. And since both quantities depend on extinction, we can rewrite this in the following way, and we can see that the star formation rate is basically related to the Schmidt law times the cloud PDF. So you can write that down as above, and you find that the star formation rate is actually a power law of extinction. And here I've plotted the sort of cumulative fraction of protostars, or you can think of it as a cumulative star formation rate in each cloud as a function of extinction. And you can see that it's flat in both cases and falls off fairly rapidly at high extinction, which is somewhat of a surprise. And if you remember from the previous slide, in all cases, the slope of the PDF is steeper than the slope of the Schmidt law, and that means that that power law index is negative, and you get very sharp fall-offs of a star formation rate with extinction. And you come to this interesting conclusion that high extinction material contributes relatively little to the overall star formation rate in a GMC. However, if you look a little bit more closely at these diagrams, you find that about 90% of the star formation is represented by the distribution of protostars occurs at extinctions greater than AK of about 1 magnitude, or visual extinctions of above about 8 or 9 magnitudes. That's still pretty high extinction gas. So that then led to the idea that we might have a correlation between the star formation rate, the global rate, and the total amount of dense molecular gas, and that you see here from our 2010 paper. We did find a nice linear correlation. We found the star formation rate is most directly correlated with dense gas, say, as opposed to low density gas. And moreover, that linear line gives you a nice time scale for the gas consumption or depletion time of about 22 million years in the dense component. We also found that, in fact, that linear correlation actually extends very smoothly to what has been known by early work by Dow and Solomon for galaxies as a whole, whether they be disk galaxies or Lurgs or U-Lurgs. They all fall in the same kind of correlation with a very similar time scale of a few times 10 to the 7 years. Now, you notice there's a gap between the local clouds and what we see in galaxies. And yesterday you heard Tom Senning tell us about looking at very massive clouds in the inner galaxy and seemed to extend this relation up. One way to also look at this is to remember that each of these boxes here is the average over an entire galaxy, is the average over many clouds like this in an entire galaxy. And I can just show you, if I just added up the local clouds, the star formation rates and masses, they would, and treated them as one point, they would be here. And if you did 3,000 of these things, roughly the number of star formation regions in the Milky Way, you see the Milky Way was set up there. And just recently in Astro PH, I found this paper by Shimajiri et al., and it filled in this gap by looking at parts of galaxies, inner and outer part of N51, the LMC, and you can see this correlation works very nicely over many scales with roughly the same gas depletion time of 22 million years. Now I'd like to finish the talk by showing you something that I found pretty astounding, also a very recent result, is that not only does this linear relation between dense gas and star formation rate extend to scales of entire galaxies, but it also extends down to the scales of circumstellar disks. And so here what I've plotted is the, actually comes from a paper by Mendeguti et al., the class 2 sources in Lupus, where they measure the accretion rates, which is the same as the star formation rate, versus the disk mass measured by ALMA observations. And you can see it fits very well on this correlation, that it seems to cover something like 15 orders of magnitude in scale, again with a time scale of order a few times 10 to the 7 years. Now these authors offered a bottom-up hypothesis to explain this diagram, which I say when they sent it to me, when they first had it before the paper was written, I didn't believe it, but the more and more I got into it, I thought it was a very interesting correlation. So according to the bottom-up hypothesis, the star formation rate at any of these scales is just really the sum of the accretion rates of the young stellar objects in a region or a cloud or galaxy, whatever. So that, again, each one of these boxes, you add all these things together, and in theory it should move you up to one of those boxes. And so that, in fact, that works for local clouds very well. This kind of bottom-up idea, where you're just adding things, would naturally explain the observed decrease in scatter of the scale, because at each different scale you're averaging, in the green you're averaging all the local star formation rates or accretion rates, and then when you get to the galaxy scale you're averaging all the clouds, so you get a natural decrease in the scatter. And if you fit this, which let's say a single correlation, again, you get this interesting depletion time of about 30 million years, and it's within a factor of 3 for all the different scales. But there is one problem, if this hypothesis is right. It would say that the sum of all the disk masses of particularly protostars, when you add them all up, it should give you the mass of the gas that we're measuring as dense inside GMCs. And in fact, that's not the case. It falls quite a bit short. So the only way sort of a bottom-up idea like this would work, seems to me, would be if the accretion rates of protostars, which dominate the accretion rates of all stellar objects inside a molecular cloud, if the accretion rates of protostars are set by processes acting on scales that encompass masses of order 5 to 10 solar masses, then this would all work out as a nice single explanation of how the star formation rate varies with density on all scales. And I'll just remind you that yesterday Phil Maher showed this slide that goes back to 1998 from Mario Tafalla and Phil, where they mapped the infall motions around the dense core L1544. And at the time, it was very surprising to see that the infall motions were extended over fairly large volumes of space that go beyond just the simple protostar in the middle. And so it's not completely crazy to think that the mass accretion rates of protostars are set by processes occurring on much larger scales than the tiny protostar itself. And this has also been something that there have been theoretical papers written that suggests that this could happen. For example, if rotation is very important in the collapse of material onto a star, then the rotation is basically set by where the material starts out with, and that could somehow control the protostellar accretion rate. So anyway, with that last intriguing bit of new data, I thank you for your attention.
Thanks a lot, Charlie. So questions in the darkness here. Do we have light? Let's get light. Yeah. So are there questions? Please, please.
It's definitely tempting to, I think, overinterpret the last slide here showing the protostars fitting on this, amazing, however many orders of magnitude that was. But if you look carefully at, there's 5 orders of magnitude spread for the protostars in some cases. So it's
the accretion rates there are a couple things going on there. One is that accretion rates are variable, so you're really worried about the sort of mean accretion rate. So you're going to get some scatter, and in fact a lot of that scatter is real. I mean, it's not. It's the protostellar accretion rates are they vary and they.
Yeah, I'm sure it's real. It's just putting it on this log plot over that many orders of magnitude. It looks when you zoom out really great, but when you zoom in, you have a huge scatter plot. It doesn't really look even.
Well, it's not, you could it's hard to
I'm talking about
yeah,
blue points,
right, but you just can't plot anything on any property on there and have it fit this way. So
yeah, I think it's interesting. It's right centered on it.
Yeah.
It's kind of interesting. Yeah, the scatter is crazy huge, but
for example, I could plot this. If I plot the same plot, there's a famous diagram, I'm told, in studying this, that there's a relation between the accretion rate of this and the mass of the star, and it's nonlinear. I think it was as m squared. So I plotted that on here, and I can't dig it up here, but if you put that on here, you find a couple of things here with a slightly different slope. So it's not just the fact that we've gone over so many orders of magnitude that you think almost anything would correlate with anything on a scale like this. That doesn't happen.
Yes?
Could you go back to the diagram where you have your dense gas star formation rate in Chinagiri?
This one?
Yeah. So the problem is that you cannot get barely starting to be able to make these plots. The problem here is on the left-hand side, of course, you use some very standard textbook and back-of-the-envelope calculation to compare your dust-based masses with the HCN-based masses of galaxies. What Shimagiri et al. Are doing is they try to align dust masses and HCN-based masses, but they are only doing this in the very, very centers of molecular clouds. While what you actually have to do is you have to map them on degree scales. The problem is that you get a lot of diffuse HCN gas far away from star formation, which has nothing to do with star. So if you take that into account and make these plots, you actually see a significant offset between the galaxies and clouds.
Well, no, I think what I read in their paper, again, it's just a recent paper, was that effectively what they're saying is that, yes, HCN is extended and you see it coming from diffuse gas. But the way they worked it out was that, in fact, the amount of HCN that's associated with dense gas happens to correspond with the ratio of 10, the alpha of 10 that people have been using anyway. For example, when we measure this same ratio in the California cloud, this alpha for converting HCN into total mass, the alphas that we get are in the hundreds. And it's not 10, which is the thing that was used, as you say, up there. I thought what was innovative about this paper was they explained that as due to the fact that if you talk about the total amount of gas that you're measuring with HCN, the alpha is much different. But it just so happens that if you're only interested in the very dense gas, an alpha of 10 just happens to come out to be correct. I don't know if I believe that or not, but I'm just showing the data.
If I do the same thing in Orion, I get a significant
could we have a last question for Eric?
Well, it's probably very short, because there probably isn't an answer to it, but I was kind of intrigued because here you have this hypothesis that star formation rate is controlled on scales of 5 to 10 solar masses. There's another hypothesis, or there's a correlation between the star formation rate of the galaxy and the halo mass, which is a rather different scale. And I was wondering if you could explain that.
No,
I wonder whether that's an unconference session.
That's an interesting correlation. Actually, I'm unaware of. I could explain the other ones I showed you. I can do that later, but that's a new one. I'm not aware of that one. Huh? Yeah.
All right.
I mean, just on that point, isn't there a correlation, like with, so if you have higher mass halos, you're gonna have higher stellar masses. We're also gonna have AGN be the one that's to suppress star formation rather than feedback. So, is there a correlation between like that with is that where the halo mass correlation with stellar mass correlation comes in?
Well, I don't know this. I'm not an extragalactic astronomer, but if the halo mass correlates with the disk mass, stellar disk mass, we already know that the stellar disk mass correlates from the star formation main sequence with the star formation rate. So that's easy to explain, but you know, what's the chicken and what's the egg? Is it the halo mass that's driving that, or the stellar mass? I mean, I have to think about that.
Okay, let's end your talk with a halo mass. Thank you, Charlie. So we have another session of introductory talk. So it's John, Jonathan, Kara, Catherine, and Stephen. So it's again to your laptop, I believe.
Yes, sir.
So you have the starter.
It has to be parents happy one.
2 minutes. You know what 2 minutes. Turn the light down.
Yeah, let me just get my computer connected first. Are you first? You can be first.
So John Lewis is our first one.
I'm not going to be talking about large-scale galactics.
Oh, yes. Well.
That I'm not an expert. Are you using slides? Yes. Okay.
Yeah, I just had mine up because I was working on them.
Okay. I can certainly try, but
it's okay. I won't make you.
Give it a chance.
So I'll turn the light
Maybe that's
down.
for the next time. We speak about the others.
I'll turn the light down. Tess, you're still a science communicator?
It's actually like the cover photo for our our YouTube cast feed. Apparently, they just took my cat and they made that the image. There you go.
Okay. So hi, this is not the right one. Hi, so I'm John. I'm a graduate student working with Charlie Latta here, studying the California molecular cloud in CO and with Herschel. And so Charlie and his collaborators completed a survey in 12CO, 13CO, and C18O of the California molecular cloud a few years ago, targeting primarily what they saw as the densest gas above AV of 3 in the nicest extinction and near-infrared extinction maps. With the Herschel maps, we know that the extinction goes much higher and is spread out a little bit more, but it's still a significant coverage. And the goal of this survey was to study the variation in the X factor in the California molecular cloud and also to use it as a test bed for testing theories of star formation, because you have 3 different regions with very different star formation rates. This one has a lot of star formation. This has a little star formation. This has a very little. Because it's called California, I also have a whole mapping scheme that you can ask me about for California and what cities correspond to where. And so for the X factor, you can just plot WCO, so the integrated intensity of the 12CO versus the V-band magnitude, plot those versus each other, and then I can color code the data points by the Herschel dust temperature. So this is derived from the Herschel extinction, the Herschel the Herschel band passes. And you can see that and I plot the canonical XCO in black.
And you can see that there is no unique X factor in this cloud, and it's a mess. And in particular, down in the cold material, the X factor nearly goes to like infinity, and this is due to there being a lot of depletion. And then the hot material, which is right now mostly dominated by the Lick-H alpha region, which is a large ionized H2 region, you do get an X factor, but it's steeper than what we normally use. And so we can map the X factor. So this is the 12CO X factor in gray with extinction contours overlaid. And since we have different bands, we can also do 13CO. And so we can see that it traces the extinction well. And with a couple of simplifying assumptions, we can convert that X factor into a depletion map and measure depletions going over 30, or at least certainly over 20, being depleted by a factor of 20, and peaking around 5. And so, yeah, we did this for the entire cloud, for everywhere that we have 13CO. And if you have any questions or comments or ideas, let me know. Thank you.
So, Tony, it's you. Me? Next one. Yep.
Even darker than this, or is this?
No, I think that should be fine. Perfect. Okay, so hello everyone. I'm Johnny Henshaw, postdoc at MPIA. So I tried to summarize my research into a single sentence for you. I'm interested in the dynamics of molecular clouds, and as we've seen already in this conference, many of you who have given talks have mentioned this in some capacity or another. And so this is really a key ingredient in trying to understand how molecular clouds begin to actually collapse and form stars. So I'm interested in many different environments, but an environment that's of particular interest to me is the central molecular zone of the galaxy. And the reason for that is that the gas conditions towards the center of the galaxy are so extreme that it really allows us to test our current best models of the star formation process and perhaps even begin to see where they might break down. So what you're looking at here is an individual cloud within the CMZ. It's called the BRIC. Many of you will have heard of it, no doubt. And this cloud is a bit of a puzzle. It has 10 to the 5 solar masses of material, radius of 2 or 3 parsecs, and shows very little signatures of active star formation activity. And so what you're looking at here are the result of 2 algorithms that I've devised to try and extract kinematic information from molecular line observations, velocity information. So the first of those, Scouse, this is published, publicly available, is a spectral line fitting algorithm. So all the blue data points that you're looking at there are referring to the location and velocity of individual Gaussian components that I've extracted from all of the spectra towards the cloud. The second algorithm, Leodis, this isn't published yet, is a way of really categorizing all of that velocity information. And so this is based on statistical hierarchical clustering, and that's the red grouping of data points there. So I'm using these 2 techniques in tandem to really try and, in this particular case, categorize the turbulence within this cloud. And the question that I want to try and answer is, how do you take the mass of Orion and to squish this to within a comparatively small volume and stop it from forming stars? And so if you're interested in that project or either of these 2 algorithms or whatever, then come and have a chat.
What's the answer?
Ah, well, TBD.
We have more, I was too early. Sorry, we have more to come, so Kara.
Sorry. That's okay for you. Thank you. All right, well, so while Catherine's doing that, I'll just say hello. I'm Kara Battersby. I just started at the University of Connecticut. I'm a new professor there. We're starting a new astronomy program, so hopefully you'll see a lot more people coming from University of Connecticut. That's currently a physics program. I apologize to everyone for missing some of the talks earlier this week. They looked really awesome. I was teaching today, and grant proposals due on Wednesday. I'm not going to bore you with the details, but I'm really happy to be here now. My research focuses on 2 main areas, and both of them I would say I focus on sort of connecting the small scale with the large scale. So on the top here is looking at the bones of the Milky Way, which Catherine's going to talk more about in a minute here, and I guess we'll have an unconference session on this tomorrow, hopefully. But so this is the idea that there are these extremely long, extremely thin, velocity coherent filaments in the galaxy, and we don't really know
where they come from, how they formed, how long they last, and what their role is in galactic structure. We happen to think that they might be correlated with the spiral structure of the galaxy, and so we're trying to understand that. So on the large scales, by looking at large surveys of the galaxy, which is what Catherine has done, and also on the small scales, this picture on the top right there is a detailed image of the Spitzer 8 micron in the grayscale in the background, and some new EROM data that sort of shows this beautiful velocity coherent structure along these little clumpy little filamentary pieces there. The second main area of my research is the central molecular zone of our galaxy, which, as Johnny has already introduced, is extremely interesting because it's an excellent test bed for testing star formation in our closest, most extreme environment. And so on the large scale, I'm trying to understand basically what the structure of the galactic center is on this large scale and how that connects with the small scale. So on the bottom here is a Herschel column density map, and then looking at the PDFs of all these different structures, you can see that all of the highest column density gas in the entire region comes from the SAGP2 complex, and that has also the shallowest power law, whereas the region off to the left there has sort of the steepest power law, so probably not forming nearly as many stars. So that's sort of understanding the large scale picture. And I'm also leading this large survey, which Perry talked about briefly, CM Zoom with the SMA, looking at in detail how the star formation is proceeding inside of there. So happy to talk to you guys more about that. Thanks.
Thanks. Well, the next one is Catherine.
Hello, everyone. My name is Catherine Zucker, and I have been working for the last year and a half with Kara Battersby and Alyssa Goodman on mapping the physical properties of large-scale galactic filaments in the galaxy. This whole project started with the discovery of a very special filament in the interstellar medium called Nessie, which you can see right here in extinction. And not only is Nessie incredibly long and skinny with an aspect ratio greater than 300:1, but if you analyze its orientation in PPV space, it exactly aligns with the Scutum Centaurus arm, which leads us to believe that it's a dense spine of this arm, and it's tracing some aspect of spiral structure. And so this result is obviously exciting, and so as a result, there's been a lot of follow-up work both by people here and at Heidelberg on trying to find more of these large-scale filaments and mapping their physical properties. As you can see here, there's a huge diversity in what these filaments look like, and that's because we've used very different selection criteria and methodology. One neat result I just want to highlight is that if you actually look at the molecular envelopes, the molecular cloud environments around these filaments, they actually follow the same star formation law as nearby clouds. However, what we're really interested in is the potential of these filaments to trace spiral structure. And understanding that, given this diversity of filaments, is very difficult because, like I said, we used very different selection criteria and methodology. And so what we've done here at Harvard is we've done the first comprehensive reanalysis of the physical properties of all large-scale filaments in the literature using the same data sets, techniques, and spiral arm models, so Mark Reed and Tom Dame's spiral arm models. Specifically, we've analyzed all these filaments using Herschel data, and so you can see this is sort of a more comprehensive view of how these filaments relate to each other. And so what we found is that the different names that we have for these filaments is not just an issue of semantics, but it could be indicative of differences in their underlying physical properties. And there seems to be some filaments that are very high aspect ratio and very dense, which could potentially trace spiral arms, while other categories could be elongated dense core complexes or very high aspect ratio molecular clouds. And so we want to know whether some populations could evolve into other populations or evolve into or from different populations, and what do their common physical origins or lack thereof mean for tracing the spiral structure of the galaxy. And so we're going to do that via simulations with Rowan Smith and a repo using magnetic fields and supernova feedback and self-gravity and spiral potential, sort of piece together which filaments are tracing spiral arms and which are sort of just run-of-the-mill filaments in the galaxy. And so I just want to leave you with a summary of spiral arms from Mark Reed and Tom Dame, and then CO from the galaxy, and then all of our filaments. And so I'm just going to do a flyby for you. And so this paper will be on the archive soon, and we're going to have it on conference, like Kara said, tomorrow. So please come to that if you're interested. Thank you.
And thank you very much, Catherine.
Oh, it didn't go. I'm sorry.
It's yours.
Sounds good.
Thank you. She's like the cover photo for our YouTube newsfeed. Like apparently they just captured her face of all the talks, and so now it's like the cover photo. yeah, we should.
All right, I'm Stefan Portillo. I'm a graduate student working with Doug Finkbeiner. And I just wanted to quickly introduce a project that we've been working on with collaborators, including Blakesley Burkhart here. And we've been thinking about measuring the 3-point correlation function of the turbulent ISM. So why might you want to do this? Well, the 3-point function is the real space the real space equivalent of the bispectrum, and it includes non-Gaussian information like phase information that you might miss, that you will miss with the power spectrum. And traditionally, the 3-point correlation function has been very expensive to calculate, going as n cubed of the number of data points you have. But a former student here, Zachary Slepian, came up with a fast way to calculate the 3-point correlation function that only scales as n squared. And the thing about the 3-point correlation function is you can think of it as an excess or deficit of triangles. So it's a function of three things: 2 triangle side lengths and an angle, giving you, these nice colorful plots here at the top as a function of 2 radii and some projection onto an angle. To make it simpler to look at, imagine just slicing along the diagonal of this plot and seeing how those quantities vary as you change the properties of your simulation. So we've shown that this 3-point correlation function statistic can actually help you tell the difference between supersonic and subsonic simulations. And there's actually a nice continuum as you go between these two states. And it also has some sensitivity to the magnetic field configuration. We can tell the difference between subalfenic and superalfenic simulations. So that's all I wanted to say about this project. Talk to me if you want to know more.
So that was our second round of introduction talks this afternoon, and now we have another research talk. Chris Bailey, it's yours. And this gets extragalactic. Yes, that's true. After Sarah yesterday from Heidelberg to Harvard, he's doing the other direction from Harvard to Heidelberg soon. So that's really bridging the gaps. That's true. So is this turned off? I just pressed several buttons.
Seems fine. Okay, hi everyone. Thanks for the opportunity to speak here. I am a graduate student here at Harvard, and I'm going to be defending my thesis in a little less than 4 weeks. So that's why I haven't been around very much, but I'm glad to be here now. And I'm going to tell you a little bit about my thesis work, which is studying giant molecular clouds in an external galaxy, but at very high resolution, so that we can do a nice comparison with the detailed work that's been done in the Milky Way and a few other nearby galaxies. So this is work I've done with Charlie Latta here, turning him into an extragalactic astronomer, despite the fact that he says otherwise, and also Jan Forbeck at Hertfordshire. So I probably don't need to convince this audience that GMCs, giant molecular clouds, are important. They are where all stars in the universe, or most stars in the universe, are known to form. And so understanding their properties, their formation, their evolution, their physics, is of key importance to understanding the evolution of galaxies. This is particularly important now because new facilities such as ALMA have allowed much larger samples of GMCs to be assembled. This is the PAUSE study of M51, which is almost 8 megaparsecs distant. And each little ellipse here is an identified giant molecular cloud. So there are literally thousands of clouds in nearby galaxies that can now be studied. So the key science questions I'm going to try to talk about, I would love to say that we can observationally study the formation, evolution, and physics, dynamics, kinematics within GMCs. That's unfortunately something you can only do in simulations. Observationally, we're stuck with scaling relations as a window into the physics that's going on inside of GMCs. So I'm going to focus on those empirical diagnostics. What are the nature of GMCs in spiral galaxies, the Milky Way and other galaxies? Are there universal properties or scaling relations? Like I just alluded to, how do the scaling relations compare between galaxies? And are there certain properties of galaxies, either extrinsic, large-scale properties, or local environmental properties that seem to control GMC formation and evolution? So what do I mean by scaling relations? So these are the well-known Larson relations, such as the scaling between the size, total size, and line width of a GMC, first shown by Larson in 1981 and studied many, many times since then. Here's an example from the 80s where you see on the x-axis the size and the line width on the y-axis, and a scaling exponent of about 0.5. And this is said to be consistent with a turbulent cascade of energies from large scales to small scales. The second scaling relation, and you can actually formulate these in a number of ways, but this is the way I'm going to formulate them today, is that the mass scales as the size. You can see in the lower right here, size on the x-axis, mass on the y-axis, and an extremely tight correlation seen in local Milky Way clouds, studied by Lombardi in 2010 using extinction. And the exponent here is 2, which suggests a constant surface density of GMCs. Is this a universal property of all GMCs, or is it only constant in the local universe? That's a question I'd like to explore. And then finally, the third law is the relationship between either the mass determined from a line such as CO, or the CO luminosity, and then the virial mass, which can be calculated from its size and line width. And these two quantities have been shown to correlate in GMCs. However, it's not that simple. There are a number of dependencies that have already been shown even up until now in the Milky Way. For example, here's the size-line width relation for a number of clouds in the Milky Way, and it's not just one relation clearly here. You have many different regions of the galaxy, and each region seems to have its own scaling relation, or perhaps lack thereof. In particular, the galactic center, which has much higher line widths, is highly offset compared to the rest of the galaxy. There's some other dependencies. Here's an extragalactic study from Alberto Bellato and collaborators in 2008. And this is again the size-line width relation. And dwarf galaxies seem to follow a steeper relation overall than the Milky Way and other spirals in the local group. Although I'll note that the exponent they derive is about the same, 0.5. Also comparing M33, M51, and the Large Magellanic Cloud, Hughes et al. Found that each galaxy occupied a different sort of locus of points in this size line width space, where in particular M51 had higher line widths for the same sizes as clouds in other galaxies. So there appears to be some dependence on the galaxy, but why that is has yet to be explained. There are also dependencies on the method used to calculate these properties. Mark showed that if you recalculate the Solomon et al. Masses using local thermodynamic equilibrium assumptions instead of virial masses, you can get quite different values for their surface densities. And I wanted to flash this plot too because I'm going to come back to it a little later in the talk. There's a number of others. I'll just talk about one more, and that's just in the method of computing the properties for extragalactic clouds. So this is from Colombo 2014. This is again PAWS, so M51, where they achieved about 30 parsec resolution. And these are the same clouds, or the same data, excuse me, but decomposed in a number of different ways. So each row shows a different correction made, or a different assumption made in the C-props decomposition of the data. And the vertical columns are different regions within the galaxy. And the R values in the lower left is the degree of correlation. So you can actually change the exponent of your size-line width relation simply based on how you calculate the properties of the clouds, which shouldn't be too surprising actually, but it's very important to consider when, especially doing extragalactic work at low signal to noise. So this brings me to what I've been doing for the last several years, which is to go to one nearby spiral galaxy, NGC 300, and to try to do a comprehensive analysis of the GMC population there. One of the main issues with the Milky Way is that we can't go out very far very reliably because we're in the disk of the galaxy. So actually going to another galaxy is helpful in this regard. All the clouds are at the same distance, and so their properties will be relatively more accurate compared to one another. And we want to go to a nearby galaxy because we need to reach GMC scales, which can now be done with interferometers such as ALMA. So here's some of the properties of this galaxy. It's about 2 megaparsecs away. It is significantly smaller than the Milky Way, about 1/10 the mass and 1/10 the star formation rate. It's in the south, so accessible to ALMA, and it's about half solar metallicity on average. So we first actually targeted this galaxy with the APEX single-dish telescope, and that's what the blue circles on this upper plot show, all the regions in the galaxy we were able to observe there. And detected CO in many positions. These were then candidates for follow-up studies with interferometers where we could actually resolve the GMCs. We started out doing this with the SMA and received a lot of time, about 60 hours, to study 10 sources in detail at 35 parsec resolution, and to get sensitivity down to about 50,000 solar masses. So this is what some of our integrated intensity maps look like in CO2 to 1, I should mention, just scattered around this plot. And I won't talk too much about this because I'll show you the ALMA data, which gives us an even larger sample. But I'll also flash up our Larson plots. On the left, the size line width relation. In blue are our results. And in black and green are the Milky Way and M33 GMCs, with the canonical relations shown as lines. And on the right is the mass size relation. And we find essentially indistinguishable relation in NGC300, but a lot of scatter and very few data points because we weren't able to resolve very many clouds with the SMA. So this served as a good pathfinder for the ALMA study, in which we targeted 50 regions, up from 10, at 10 parsec resolution. And we got some really nice data, like what you're seeing here in the lower left. Here are some of the statistics of our study. Of the 50 regions, almost all of them had many, many clouds within them. So at 10 parsec scales, there's a large amount of multiplicity, up to 10 to 12 clouds per region. In the lower left, you can see that the signal and noise is relatively high. The red sample is the one that you'll be seeing data points in the plots I'll talk about in the following slides, so you can focus on that. This is really key for extragalactic work because you need high signal to noise to recover the properties of clouds accurately. So here's the SMA image again, and I'll just show you the same region now observed with ALMA. You can see the sensitivity and resolution are quite a bit higher, although the spatial coverage is not as good. And the morphology of the different regions we found is actually quite diverse. Anything from large, very massive complexes of clouds to strings of small objects to long filaments. And we were able to analyze all their properties in a consistent way. There are 250 clouds in our sample, and to find those, we used a package called CPREPS. And I put the recipe up here because that's all it is. It is one way to look at your data and decompose it into objects. And the steps include first identifying the clouds, and then you have to characterize their properties, their sizes, their line widths, their masses. And I can talk about this more in the questions if anybody wants to know. Just looking at those properties now, size, line width, mass, and surface density across the galaxy from the inner regions out to about 3.5 kiloparsecs, which is as far as we go. We actually don't see major trends with radius, which is somewhat surprising in the context of Milky Way work, where you can see that in the outer galaxy there are much lower surface densities. However, I would point out that we only go out to 3.5 kiloparsecs, and even though the galaxy is smaller, that still would put you about in this regime compared to the scale length of the galaxy. So that may actually not be that significant and may be consistent with the Milky Way. The mass spectrum we find has a slope of about minus 1.8. This is consistent with the Milky Way, although slightly steeper perhaps. More significantly, there is a clear truncation in the mass spectrum that we found, which has also been seen in other studies of GMCs of the Milky Way, but is generally not seen in the outer regions of galaxies, actually. In comparison to a couple of other nearby galaxies, again, M33, a truncation seems consistent, and the slopes that are found in these other two galaxies are consistent with what we find for the inner of M33 as well as the LMC. here's again the SMA plots, and I'll just fade in the ALMA results, which provide significantly more data points and better dynamic range. We're able to formally fit these relations, and I'll just have to do that again. You can see that we get a size line width relation and a size mass relation that are completely consistent with what we find in the Milky Way, a slope of 0.5 and 2, respectively. I said I would talk about this plot, but I'm going to run out of time, so I'll just leave it as a discussion point for later. I want to finish the talk by talking about what might be controlling properties of GMCs. You can see the Milky Way and NGC 300 have very different stellar masses and star formation rates, morphologies, and metallicities, and yet it seems like the GMC properties are pretty much the same. So what could be controlling this? To test this, we compared with the galaxy M51, which is not too far in the galaxy main sequence from the Milky Way, but is a liner and interacting galaxy. And it's been well studied by the PAUSE survey. So comparing the surface densities on the left in histogram form, M51 is in red, and where the colors overlap, you can see a color change. You can see that M51 has much higher GMC surface densities, and also on the right, a much higher size line width relation coefficient. So here we are actually seeing differences between the NGC and Milky Way on one hand and M51 on the other. And this isn't an effect of resolution. I've just now added green points here, which are what happens when you take our data at 10 parsec resolution and smooth it to the resolution of M51, which is 40 parsecs. And the relation holds even at larger scales, and the offset persists. So there must be something else going on. And in this paper that should show up in AppJ very soon, we think it's actually the mid-plane disk pressure that may be controlling these GMC properties, like the size line width coefficient and GMC surface densities. So if you just calculate this for NGC 300 in the Milky Way and compare it to M51, there's a clear difference where the higher pressures in M51 may be leading to compression of the gas, higher surface densities, and therefore a higher size line width coefficient. So I'll leave you with these and take your questions. Thank you.
Thank you very much. So questions, please.
Let's get some light.
Sure. Yeah, at large scales, you're saying.
The galactic center, for example, yes, on the large scales you get a lot of turbulence, but if you go down to the scale of dense cores, it's actually not, even in the galactic center, it's not so much different from towers,
right.
Surprisingly. So here you have now data set where you can do that in the galaxy, where you can go down from, I don't know, something like 50 parsec to 10 parsec for the same region. What happens if you connect those data? Do you still get a power of 0.5 or?
Yeah, you can fit the green points and you get the same exponent. You can see on the plot here they're right around the blue line is the line fit to the blue points, but the fit to the green line is almost the same.
What I mean is if you have specifically one green point to which several blue points.
Oh, I see. So that's been done in the Milky Way. We haven't heard that. That'd be interesting to see. It's typically only 2 or 3 blue points per green point. But I'd be curious to see where those lie. I haven't looked into it. Thanks for the suggestion.
All right. Chris, could you show the slide that you skipped?
Yes. Thank you, Mark.
You must have a question to the slide.
Well, I have to see it first. And,
so these are our data in blue,
yeah.
And Mark's data in black, with M51 median for all their clouds in red.
So you do see the trend?
We do see the trend, yes. And I've even started to look into whether there could be any fact that the axes are correlated going into this. And it looks like it couldn't produce a correlation this strong, but I'm still working on that right now.
So I would have a question to your very last one. So what causes the different midplane pressures? What's the reason for this? The underlying one?
So I could speculate or I could tell you what we did. So I'll do the latter first, which is to just, the pressure as formulated here just comes from the gas and stellar potentials. So their surface densities and their velocity dispersions. But what controls those are probably other factors, and it may be that this galaxy interacting plays a large role in changing its dynamics in this way. It also is a much stronger, has much stronger arms than either the Milky Way or NGC 300. It's a very, very obvious grand design spiral. So the stronger spiral structure might also be playing a role, but that's speculation.
More questions? If not, then let's thank Chris again. And we get to our last round of introductory talks. So it's Garrett, Diana, Josh, and Mark. Please come to the front, and we have Catherine again. The cat is coming up. The needed cat. She is missed.
All right. So, hi, everyone. My name is Garrett Cardo-Keating. I'm a SMA fellow from just across the street here at CFA. My main research interest right now is actually trying to understand the evolution of molecular gas over cosmic time, kind of in particular trying to understand how it goes from this very primordial and pristine gas from the very early, very first galaxies post-recombination to the very smoggy, dusty material that we see in our local modern galaxies. And I'm interested in doing this observationally, which means that I have to figure out clever ways of doing this efficiently. So on the left-hand side, I was told to supply an image for my badge that was an interesting, stimulating image for discussion. And what better an image than blank sky? Of course, I think everybody here knows there's no such thing as really truly blank sky. And in fact, it doesn't matter what patch of the sky you look at. There are going to be lots and lots of potential sources to look at, in this case, galaxies that I'm interested in. And so the question that I have for at least myself is, how do you extract all of this emission that's out there just waiting to be detected? And so I'm working with a hybrid of methods using kind of direct detection and stacking techniques, which are kind of traditional techniques for looking for faint objects, as well as this intensity mapping technique. It's a power spectrum technique very similar to methods that people in the CMD community use, with the idea that instead of detecting individual objects, you're looking to detect the aggregate power coming from, or aggregate emission coming from lots and lots, thousands or millions of objects. So this isn't just a hypothetical idea. This is an actual survey. In fact, 2 surveys. So the first survey using the Karma telescope is that COPS data point that's over on the left-hand side. And we've started a new phase of this, trying to use the rotation ladder of CO to try to trace out and probe the molecular gas from lots and thousands of galaxies between redshift 0 to 6, using the VLA, the ALMA compact array, and the SMA all combined together. We just finished our pilot survey and just got the green light for doing a large-scale survey, 500-hour survey with the SMA. So stay tuned. And hopefully with this SMA data, we're looking to do lots and lots of really exciting, cool science, including actually exploring the connection between halo mass and star formation rate by way of molecular gas, as well as other interesting topics that 2 minutes does not afford me to discuss. But I would love to talk to anybody who's interested over bowling or coffee or whatever. Thank you very much.
So hi everyone, I'm Deanna and I'm working with Chizu studying the disk and wind kinematics around the star MWC 349A, and we're doing this using hydrogen recombination line masers. And why is this interesting? Well, stars evolve and gain mass through accretion from disks around them, and in order for accretion to occur, there has to be some loss of angular momentum. And it is believed that jets and outflows might be the cause of this loss of angular momentum. But unfortunately, spectra of jets and outflows are broad, and so this makes them hard to study. And in our case, we're fortunate to have the strong maser emission. And so this allows us, using SMA data, to get high-resolution data, and we can, using centroid fitting, get position plots for the masers from 31, 30, and 26 alpha transitions. And if we are to create a rotation curve from this position data, we get a linear feature, which is consistent with Keplerian motion. And we see an interesting inverse slope relation between the quantum number of the transition and the slope. And so, as you can see from the expression here, the slope is, it gives us information about the star. And also another thing to mention is that the lower quantum transitions occur in inner regions in the disk where the density is higher. And so we hope to use this to better understand the object. But, and there's always a but, we have acquired recent modeled data from Alejandro Rubio, and the model has given us insight and suggests that the analysis of these rotation curves might be more complicated than expected, and this has to do with the addition of disk and wind components. And I'm happy to talk more about that if anyone has questions, and I'd love suggestions as well. Thank you.
The next one is Josh.
Okay, so hi everyone. So my name, I'm Josh Spiegel. I'm a graduate student here at the CFA, and so I'm a little bit of an outlier here in the sense that I have done work. I'm very interested in star formation in terms of galaxy evolution, and so what my biggest work a couple of years ago was trying to look into essentially a meta-literature study of this star-forming main sequence, this correlation between stellar mass and star formation rate. And as part of that project, I sort of became increasingly paranoid about the methods that people actually use to estimate many of these quantities. And so that ended up leading me on this long saga where now essentially I'm more of an statistics guy and do a lot of my thinking now about Bayesian inference and all its sort of applications in astronomy. And so day to day, I work on some changing linear combination with Daniel Eisenstein, Charlie Conroy, and Doug Finkbeiner on a wide range of scales. In particular on sort of three problems, essentially how do you estimate your parameters, theta here in a given model, m for some data set that you usually have. So how to do that effectively, how to do this in a hierarchical way so that when you have noisy data, you can actually infer underlying populations, which is something that many people are usually interested in. And finally, I've been very interested in trying to merge sort of machine learning methods with sort of statistical sampling and to come up with models that are physics-based but data-driven. So just one thing I wanted to sort of highlight here is that most recently I've been working on projects to implement dynamic nested sampling, which is a sort of new Bayesian technique to try and sample from posteriors that is more flexible than MCMC. And I've compiled this in a new package called Dynasty that hopefully we've designed it to be about as easy to use as MC, and that really we wanted to use because it incorporates automatic flexible stopping criterion for sampling from posterior distributions. So no more sort of running your chains until you have enough samples. It actually will tell you when it thinks that you've characterized the posterior well. So if anyone's interested, to please check it out. Other things I'd be happy to talk about is how exactly to incorporate hierarchical modeling into some types of problems that you have. So an example would be if you have uncertainties in some measurement that you're trying to look at, and you don't know what your prior should be, you can try and sample from both your parameters and the hyperparameters of your prior at the same time. And this has led to a lot of pretty neat results. So on the left shows what happens if you assume a fixed but incorrect prior. And on the sort of top right and bottom left show two different ways of incorporating hierarchical inference into this particular model of trying to estimate histograms in Redshift. So the final thing that I've started working on now that I'd be more than interested to talk to people about is trying to come up with data-driven SED models for a wide variety of problems from stars to galaxies, where you'd like to take your physical empirical spectra or some type of associated model, embed it in some higher dimensional parameter space, and interpolate from them in a way that gives you physical, intuitive results. And so we've started using many of these different techniques to infer lots of properties on dust and star formation rates from galaxy surveys with Charlie Conroy. And those have led to some very interesting and still in prep results. So that's all I have. Thanks.
Yeah, maybe keep it close. Oh, great. I think I have to advance it.
Yeah, you have to advance it, yep.
Okay, my name is Mark Heyer from the University of Massachusetts. Thank you for letting me come and crash your party here and be able to talk science with you for a few days. My interest has always been in understanding the motions in molecular clouds, because I think they give us the best information on the physics of molecular clouds. This is a velocity encoded image of 12 CO emission of the torus molecular cloud. I want to focus on just this region over here on the upper left. It's sort of the far outer envelope of the cloud, low column density. But when you look at a little bit higher resolution and higher sensitivity that we got from the Arizona telescope, you see these striations that are lined along the magnetic field direction. I do make a spectrogram along in that trapezoid box, so I have a position velocity diagram. You can sort of see the spectra along the perpendicular to those striation lengths. And if I kind of highlight what's happening on the striations, you see that in the profiles, they're appearing as sort of a redshifted shoulder in the line profiles. If I go in between the striations, I see it shifted to the blue shifted side. If I show the channel map corresponding to the blue shifted side, you'd see striations that would be interleaved with the striations you see in that image. So the picture we have here, you see some oscillatory pattern in the velocity. The picture we have is of magnetosonic waves propagating through the cloud, the wave is moving perpendicular to the magnetic field direction, but that causes compressions, and it would predict velocity variations, perpendicular magnetic field, and strong velocity coherence along the magnetic field, and that's exactly what we see. I'll take one slide to show you that the LMT, I've lately been moving my science to the large millimeter telescope, which is operating now. Last night was the deadline for the 50-meter LMT. On the right, or on the left, no, right, I show an Aztec map done with 1 square degree in the galactic plane, just to see what we could learn beyond what Atlas Gal and Bolocam had learned. And so these kind of images aren't that great because they filter out all the extended emission and you're just left with the compact blobs. But those are the blobs, the clumps, and the cores that are forming stars in molecular clouds. And so we've did a lot of science in that. There's a paper on AstroPH Now that describes this. And it should be on monthly notices any moment now. Thank you.
So before we start the unconference session, let's thank all the speakers of the afternoon session again. And for this unconference part, I give the chair to Alyssa.
No, we need the ledge.
Do you want chairs again, John?
Yeah. But everybody like just stand up and for a conference. Really, seriously. There's some cold coffee in the back.
That's encouraging.
I don't know.
I have it. No.
It just said, can you show Tom's email as our unconference summary?
This one?
Yeah, I sent you a text.
Are we sitting in the chair?
You are sitting. You are, Doug.
Let's just stick it on the screen. I don't know if anybody else is going to see anything. Why don't you just hook up your computer to start? Just go in like a random order. Does that have HDMI? Yeah.
Yes.
Okay.
No. It's really nice because there's, all the constraints they have from it's kind of back up. None of that. So looking at a limit, a minimum. There's always a well, no, we had idea. We can make one. Here, she's a
We'll get people with the lights. That's how we'll get their attention.
I'm not doing anything fancy and glue. I'm just trying
No. Yeah, just like slide it through and show the 3D. You have the 3D thing open?
Oh no, I had to close it. But
Can you make it anyway?
I can do it.
Now you're an expert.
Yeah. Oh, I need to ask you later. How can I plot the two lines, like if they're 2 VLCs, on the
together?
same?
Yeah. Are they on the same grid?
Yes.
Just drag them onto each other. Don't do it now.
No. Okay. I merged them. I don't know if that's.
Oh no, then you can't make them two different colors.
Oh, okay.
Yeah. Unfortunately. So you can
Well, what's your value? Here's that. We're going to what thing that we had to release.
So we had made it like 200 to 500 or something, but we have.
Okay.
In the lower one. Like make the min-max instead of, I think it was the bottom one, 200. That's good enough. Just let it hang out the bottom of the cube. It doesn't matter. Okay, I'm going to get people's attention with the lights.
Oh, there was a way to zoom this.
2 fingers. Just zoom in like, yeah. Got it? Okay, which is just the working microphone? Hello, everyone. Hello. How about if I turn off the lights and say hello? I'm so glad you're already talking, but we don't have any beer yet. Beer will be provided at the bowling alley. I believe it's included. So now we'll put the lights back on. Wait, they were right there. Hector's here. Blakesley was right there. Where'd she go?
What?
We want more.
Blakesley was there.
Hope, what are you doing?
Yeah, Hope, come on, just sit over there. Okay. But Blakesley was here like a second ago. We'll just, and Doug was here too. Blakesley and, I swear they were right there. Well, we'll just do those after. We'll actually go in backwards order, and so we'll let Hector, who's standing here, go first. Does that make sense? Okay. And so here you go.
So someone else is going to talk about the gluon conference?
Yeah.
Oh, okay. Yeah. Okay. So I was in the morning in gluon conference, and then in the afternoon we were showing, it was a show on Alma data show and tell. I'm a beginner glue user, and I can tell you I'm a convert now. So yeah. Thank you for this, even though we had some problems in the morning. But yeah, more on that later. So okay, so this is a single pointing observation of the HH4647 molecular outflow using band 6 CO2-1. This is the CO. I think it's a subarc second resolution 0.6, I believe. It's at 450 parsecs or so. So you can see all the beautiful structure there. I'm going through channels. It looks like it has different episodes, as you can see them in the different arcs there, bubble-like structure there. That's the blue lobe, and then this is a cloud massy part, and here's the red lobe. And this is something that I see in other outflows too, that the lobe that what we once used to see with a filling with all the emission, you can see it now, and it looks like very filamentary, very clumpy. This is not the only outflow that looks like that when you look at it at a higher resolution. So we have other data, 12CO, 13CO, and C18O. With glue, you can merge two data sets, and this is I learned this today, 13CO and C18O merged. So they're ones, that's C18O again, close to the cloud velocity. You can see this is very nice envelope there, and at outflow velocities you can see an C18O outflow, which you usually don't see. So that's it. We have other molecules as well, but there was somebody else in the Alma what? Oh, the 3D version, yeah. So that's yeah. Sorry, yeah. So one thing that you can do in glue is do a 3D rendering of your data. This is the CO2-1. Now this is not yeah. So like I'm whoops. Like I said, I'm a beginner. So here's that will be the classical PV diagram. But if you can move it around to look at it in different point of views, you can see here one of the shells, and maybe here one of the shells. I have to play around with the grayscale, but some of the things that you can do, maybe this and this. So this is only one outflow there that's showing. So yeah, yeah.
So you're converted.
I am converted to glue. Yes, I can do more stuff with catalogs, and that didn't work for me now, but I'll look into that later. And PV diagrams, maybe Betsy will show something about the PV diagrams.
All right, so this is a little bit further afield for a star formation crowd, but this is the very center of our galaxy. All right, so this is the circumnuclear disk around the black hole. So the black hole, you can't see it because it's a map of HCN and HNC. But the black hole would be around at the center. Up and down, it's about 4 parsec size scale. And so here again, also got a chance to play with glue today. Convert, yes, all of the
all of the sayings. But what you're seeing here is an overlay. So this is a 3D, and I'll sort of show you the position velocity in a moment, of actually showing two lines simultaneously. So the red is showing you the HCN 3 to 2 line, and the blue is showing you the HNC 3 to 2 line. And it turns out this is actually a really nice discriminant in the center of our galaxy, because one of the problems with the center of the galaxy is you're looking through a whole bunch of galaxy to see the actual center. Or in this case, you're looking at a bunch of other gas that might be merely 100 parsecs from the black hole, and we want to look at the gas that's only a few parsecs from the black hole. And so it turns out that the blue, which is the HNC, is actually picking up more of the gas that's further away from the black hole. So you can start, see if this will respond here. So here I'm starting to show some of the velocity axis here. And so you can see a lot of the features in blue now are actually features much more around, I think one's around 50 and one's around 20 kilometers per second. Features from clouds that are in front of the gas around the black hole. And then the red is showing you, again, this sort of rotation signature, plus or minus 200 kilometers per second, of gas that's actually orbiting very close around the black hole. So there are a lot of fun things you can play around with. So here, for example, you can also do the same overlay in just individual channel maps. And so you can show, again, the same thing. So you can see some of the features that show up purely in blue from clouds that are in front, and features where you see both. And then what we're playing with, you can also go ahead and make, we're making fun little plots here. So one of the things that's interesting and new in this data set is that there is a feature here. This is an extremely linear feature, which looks like it's something that actually is further away from the black hole. It's not ionized, possibly approaching the black hole. And so you can do fun things like do a position velocity cut on this one here. Not happy. There we go. Yeah, I think it's down here. Oh, we're doing a profile. That's not what we want. It's behind. Ah, there we go. So you can see a nice, for example, velocity trend. So again, a very linear feature with very linear velocity trend, linear spatial trend. So fun with glue. And ALMA.
Okay, so I just want to, essentially what happened today is we had some, So I've ran many glue tutorials, and this was the one we had the most problems with glue installations, and so we had problems with Python 2.7, and so immediately after the session we had an emergency hangout with the developer, and he was able to fix. I didn't just, we know him, yes. Oh, who you know as well, yes, Tom Robitaille. Sorry, he's Tom Robitaille. And so he fixed basically everyone's problems in like an hour, and essentially Alvaro before couldn't even load viewers, and now he's making amazing science results with glue. Oh my God, I'm so sorry. This is Hector, I'm sorry. Oh my gosh, okay. It's late for me with my intro talks. So Hector, did amazing results with his outflows, and he couldn't get it open before. And then Betsy also had some problems, and so Betsy's highlighted in this email here. Let's see. Yeah, Betsy's Mills installation, and so now it's fixed. And so, just 2 testimonials that glue is an amazing software. And if you want a backup session for, we weren't paid anything. If you want an extra session with your glue installation working tomorrow, and there's interest, Hope and I are happy to run glue version 2.0 to sort of show you more cool things that glue can do. Sorry, Hector, I know you're actually not Alvaro, so.
And this also proves that sending bug report works.
Yeah, he pulled them all up and he fixed them immediately.
So please do if you have any comments.
Thanks.
Okay, so then something non-glue. I'm sorry, I have no presentation on glue here. So we had a session about disks, and in particular about embedded disks, and the idea. Do we need no problem?
The video.
Okay, so for the video, so the idea was, or what we had in mind was to discuss a little bit how embedded. It doesn't work. Does it?
I think maybe you accidentally turned it off.
There should be a green light,
On the
a
top.
little button. You see it? You do it?
Glue is easier.
It's a bad
I'll get it there.
Glue
Yeah.
to that.
Try it now.
Okay, yeah. No? Yeah, now it works. Okay, so the idea was to discuss a little bit the similarities or difference from low to high mass. So what can we learn about the disk we think to know at low mass or low protostellar masses up to the high mass regime, what we're working a lot on. And so it was a very leisurely discussion, I would say, about the different properties and what we can do. And we looked also at different data sets. On the one hand, we were looking at the low mass case, where there is a lot of work and publication recently from Shinfei Li. So we looked at their paper, what they have done about these, they call it the hamburger disk, and where they do see the emission. And it's interesting that there is no line emission in the disk midplane, for example. There's nothing. So if what is good to trace the disk midplane in such a low mass disk? That was difficult, not easy. So that in general, we always think that the high mass case is much more difficult because further away, more complicated, more clustered, all these things. But that may be the only part where the high mass may be advantageous because it's warmer. It's not as cold in the midplane, so there we may have advantages in the high mass case that we can see even in the midplane if optical depth doesn't kill us. Okay, that's something to be determined, but which may help. So the discussion was on the one hand around these ones. Then I was showing some recent ALMA data about a high mass source at 20 milliarc second resolution, because Thomas was asking whether one sees also fragments or even spirals. Well, we don't see spirals, but in this region there is at least substructure, what one can see really in the new ALMA data. So substructure is possible to identify also in high mass regions. We try to connect a little bit the also observationally and physical properties, how far one can get with a tumor analysis, things like that. I think it was a good discussion. If you ask me for a real result, that's more difficult to put there, but I think it was a good discussion we had. Is there anything I missed? Do you want to add anything? If not, then I give it further.
All right, so we had a morning session titled Turbulence versus Magnetic Fields, a Fight to the Death. And first, before the fight commenced, we all took bets as to who would win. And I can report on, we took bets before and after. So before, Turbulence was a clear winner, was going to win. So we did a poll where 10 was, you think turbulence is the most important thing for star formation. Magnetic fields don't matter at all. Definitely going to lose the fight. And a 1 was magnetic fields are the all-important ingredient of star formation, and turbulence is not important. So the average score before the fight began was a 5.8. So that means people slightly favored turbulence.
5.5 is the middle.
Yeah, so, like I said, slightly favored turbulence. 0 to 10. The maximum was an 8, so someone really liked the turbulent paradigm, and the min was a 4. Okay, so the fight then began, and turbulence kind of came out strong from the start. We showed a number of both simulations and observations. So I showed a repo simulations that were led by Philip Motes, and basically what we did was take a repo moving mesh code with MHD, turbulence, and gravity, and kept all the parameters the same except changed the magnetic field strength. So it was really a controlled experiment to see the effect of the magnetic field on gravoturbulence and collapse from about 5 parsecs all the way down to 100 AU. And in that experiment, it was pretty clear that changing the magnetic field strength actually had a huge impact on how stars eventually would form. However, even in the strongest magnetic field case, we still saw that the collapse took place. So you could still, the moral of the story is you could still form stars even with strong turbulence, with strong magnetic fields. Juan also showed some very nice Planck data, including the Orion-Eridanus bubble region, which showed very nice ordered magnetic fields. So that might imply that the magnetic field on those kind of large, tens of parsecs, hundreds of parsec scales might set the dynamics. And I think the HRO analysis sort of indicates that things are subalphenic, which could mean the magnetic energy is at least comparable to the turbulent energy or maybe slightly dominant. And so after a long fight, we took a vote again, and the average was a 4.9. So magnetic fields took the lead.
Well, wait a minute. You did a little experiment, at least changing the magnetic field, keeping everything constant. What was your initial condition? Was it supercritical or subcritical?
Very good question. So in fact, that changed. So in 3 cases, it was supercritical to slightly on the border, but in 1 case, it was subcritical, and collapse still took place even in the initially subcritical run.
Did you have ambipolar diffusion?
No. So so there was turbulence. So there's another possibility that the diffusion can take place by the turbulent reconnection. And reconnection does take place in these simulations, and so that's something that we're actually looking into further, but that's the current idea, that you go from a subcritical to super, and in the final mass to flux ratio in the collapsed region is actually supercritical. So some diffusion had to take place, yeah. Anyway, so yeah, the jury, both sides were bruised, but magnetic fields seem to have come out slightly ahead. That's the summary.
All right. Well, this afternoon I hadn't been planning to run an unconference session, but Alyssa twisted my arm and said you should talk about mapping things in 3D like dust. And I said, that seems very self-promotional. And she said, oh, what about glue? I mean, come on. So that put my mind at ease. And so we had a nice hour and 20-minute romp through 3D dust density, 3D dust temperature, 3D RV mapping, whatever else in 3D, I don't know. And I realized at the end when Eric was asking me, so is there a way to actually get this 3D dust map, that I had actually told people. This is all online. If you go to readthedocs.io, it explains how you can type pip install dust maps, and that gives you a software package that gives you access not only to 2D dust maps you might like Schlegel, Fink, Minor, Davis, or the Planck dust map, or a few others, but even Bursting Hylas. Hey, for old time's sake. But also about 5 different 3D dust maps. There's the Marshall map, and there's a bunch of maps, so including our map. The other thing I failed to mention is that the only 3D dust map of ours in the literature right now is the 2015 version. The 2017 paper is not accepted yet, but all the information's already online. So if you're going to use our map for something, please use the 2017 version, which we hope will be accepted by a journal one of these days. If the referee's in the room, I'll give you pizza tonight if you'll accept the paper. So I don't know if there's anything else to say about that. Oh, so that was all this. And I also mentioned this, which is the DCAP survey. So in the last month, we released a survey of 2 billion stars in GRI-ZY photometry in the galactic plane in the south, observed by DECCAM. So I think it's actually the largest, in terms of number of objects, the largest optical near IR survey ever, and it only took 22 nights of telescope time. It helps if you look in the part of the sky where all the stars are, but that also tells you about the power of DECCAM as a survey instrument, which I guess I knew, but I was still very impressed with DECCAM. And I can't take any credit for the awesomeness of DECCAM. I also have comments on bowling. I don't know if I should save those till later, or should I do that well? Oh, well, actually, Catherine should say whatever she wants to, or maybe Catherine will just zoom and pan through beauty things where. So, yeah, so I kind of started this, but Eddie Schlafly really led it. I mean, he really kind of led proposal writing and software reduction and data release and everything. I mean, so basically Eddie did everything. This is a pretty big survey for one person to do single-handedly, but Eddie Schlafly is pretty amazing. And so, like I said, 2 billion stars. There's lots of dust here. This is roughly the galactic plane plus or minus 5 degrees in the southern hemisphere. Yeah, there's more stars. There's a lot of stars. Oh, well, then zoom out and find filaments. I don't know. Yeah, so it's a GRZ band mapped to blue, green, red. But we have GRIZY. So the DECCAM has about quarter arcsecond pixels, and the PSF's about 1 arcsecond typically. I mean, it varies from night to night, but it's something like 1 arcsecond. These maps have probably been binned a little bit just so that we don't spend infinite disk space on this viewer. This is a viewer written by Dustin Lang for the Decals project, which is surveying something like 15,000 square degrees of sky with DECCAM for targeting for DESI. Yeah, that's one of our favorite filaments. That's the one on my name tag. And we said, hey, Dustin, would you mind if we threw a few million images in your viewer so it's really great that Dustin did all the hard work on this viewer. And Sloan's in there, and all kinds of stuff is in this viewer, even the SFD dust map and the H-alpha map and other things. So you can play games like find a bright spot in SFD, that's an H2 region, then zoom in on it in this and see all the pretty stuff there. So that's been fun. Actually, would you mind, Catherine, clicking on, see where it says DCAPS models? So we're switching from the data to the model. Okay, and if you hit the space bar, it blinks between them, which is a great feature that I had Dustin add. So you see we're doing a terrible job of modeling the images. Maybe zoom in a little so you can actually see the difference, because if you zoom in enough, one of them has noise and one does not. That's the difference. That should be good enough. Well, I don't know. Anyway, so as you can imagine, it's hard to do crowded field photometry well enough. This is coming from California, so we have to be patient. The diffraction spikes are in the PSF, like it's all in there. And so Eddie worked really hard on this. And even if you go over to the part of the sky with those wonderful filaments in Vila, those are modeled too, in the sense that any sky background on kind of a 20 pixel scale is modeled. But it's actually 2 billion objects. It's kind of crazy. I mean, the entire Pan-STARRS survey is less than that, but this is where the stars are. And so Eddie wrote his own pipeline to do crowded field photometry with some fancy matrix and iterative matrix inversion thing that is something you can do if you only have stars. Right, so the assumption here is there are no galaxies. Occasionally a galaxy peeks through. We model a galaxy as a linear combination of stars, which I assert is not wrong, but not really, not right either. Zoom in on here.
Wait, say it again. Where?
There. It's a really nice part of the sky. Yeah, there should be lots of pretty green filaments, yeah. So, I think I know what they are, but you can poll the audience. What does the audience think those are? So green is red in real life, so it's H-alpha emission, but what's it coming from? Zoom in another level or two. They're very pretty. Yes, it's a piece of Vela. This is the outskirts of the Vela supernova remnant. And you've seen this before in, narrowband filters, and it's very beautiful, and everyone's known about it for many decades. But just the fact that it shows up so beautifully in broadband images, I just think is pretty cool. Yeah, so zoom in on, I don't know, maybe that one where there's a nice separation between the blue and the green. Yeah, so now blink between model and data, and you can... I mean, there's nothing magical here. It's just that the, he has some iterative scheme for finding the stars and then asking what the background looks like and then modeling it with some, smooth thing and just kind of iterating that. Oh, yeah, you can totally make these images with no stars. We should add that to the viewer, actually. Because if anyone wants if you want a map of the glowing ISM, we can do that. But I'm really impressed by this survey, which was just really single-handedly done by Eddie. Anyway, so probably enough of that. Should I talk about bowling? Okay. So just 1 minute on bowling. Many of you are familiar with conventional bowling with a big ball and 10 pins that are asymmetrical, and you get 2 throws and such. But who has done candlepin bowling? So less than half the room, I think. So there are 4 main differences with candlepin. The ball is small. You get to throw it 3 times, not 2. The pins are symmetrical top to bottom, so they just they're kind of like filament. Well, I don't know what a filament is. Yeah, if you compute the Legendre compressed 3-point function of the pins, then you get a different answer than you do for conventional bowling. And there are no objects, there are only fields. And then the other thing is, this is important, they fall over. I mean, if you're doing well, some of them fall over, and they don't clean up. Conventional bowling, the machine picks up the pins, wipes the knocked over ones away, and puts them back down. That does not happen here, which means the fallen pins are part of the game. And you can have a lot of fun trying to hit that pin that's fallen down and get it to hit the other pins, or maybe it's laying across the gutter and you can throw a gutter ball and pop it up and take out a few other pins with it. And so it's... So I think it should be fun. I think you can be sure. I mean, you saw the video of me. We're all terrible at this. I don't think anyone who lives here will claim to be good at this. But it's a lot of fun, so we can all go embarrass ourselves together. And the pizza's good. And there's beer.
I think they think we're going to be there at 7, but if anybody wants to show up a little bit early, I think that's fine. But you can walk there. It's kind of a medium late.
25-minute walk somewhere.
But in your hotel, if you're staying in Foursquare, is on the way. So does everybody have directions?
Not precisely on the way, though. I mean, if I were walking there from here, I would go Raymond, Yerxa, Hollis, Day, and that takes you straight there.
Nobody of us understood that.
I'm happy to lead a party that wants to walk straight there.
Is there a map in the schedule?
Is there parking?
Just put in second.
It's at Davis Square.
Google it, it'll come right up.
Is there
It's in
parking?
Davis Square.
Do you have a Somerville permit?
It's
There's no particular parking.
We have a map of it on the
Oh, there is a map. Okay.
Well, yeah, there's a lot of concerts. I don't think I've ever seen
I know. It's,
Doug has a big
Yeah. You see how tall he is? He might be able to walk like 20 or 25.
Oh, totally.
More like 30 or 40.
No.
But you have very long.
It's a trivial walk. 25, 30 But parking is challenging, unless you have a Cambridge or Somerville.
What are you heading out to walk today?
You just got lucky.